Hello. This video includes a continuation of reaction types, specifically redox reactions.
Have talked about non-redox reactions. Okay, they're called double displacement reactions. And the two type are precipitation and acid-base reactions. So now we're going to talk about redox reactions. And redox reactions are ones in which oxidation states change. And we're going to define what oxidation states are in a second. And the examples of redox reactions are single displacement reactions, combustion reactions, decomposition reactions, and synthesis reactions. So what we'll do first is talk about what oxidation states are, and then we'll look at some examples of redox reactions. So when we talk about oxidation states or oxidation numbers, they're essentially a way for us to keep track of electrons. Okay, and we're going to have some rules for identifying the oxidation number or the oxidation state for every atom in a compound. So the first rule, if we're looking at an atom that's not in a compound, okay, it's all by itself, the oxidation number is 0. If we're looking at a monatomic ion, okay, an ion made of one atom, so a sodium ion or a chloride ion, the oxidation number for a monatomic ion equals the charge on the ion. So a sodium ion would be +1, a chloride would be -1. Okay, if we talk about hydrogen, hydrogen is assigned an oxidation number of +1 when it's combined with non-metals and a -1 when it's combined with metals. And remember again that non-metals are on the right side of the periodic table and metals are on the left-hand side. And I will tell you that in most instances, hydrogen is combined with a non-metal. So in most instances, hydrogen has an oxidation state of +1. Okay, oxygen in almost all compounds has an oxidation number of -2. Now in peroxides, which is not very usual, it's a -1. So oxygen is almost always a -2. Halogens, okay, elements in group 7 on the periodic table. Fluoride is always -1. Most of the other halogens are -1 unless they're with oxygen, and then they can vary. And we'll look at some examples. Now, the sum of the oxidation numbers for all of the atoms in a molecule or in a polyatomic ion equal the charge on that molecule or the ion. Well, molecules are neutral. So the sum of the oxidation numbers on a molecule is 0. And the sum of the oxidation numbers for polyatomic ions is the charge on that polyatomic ion. So those are all the rules. Let's look at some examples. And we're going to do the first couple together, and then I'll give you a couple minutes to see if you can figure out some on your own. So let's say that we have KCrO2. And we want to find out what the oxidation number on chromium is. Well, the first thing is this is a neutral molecule. The charge is going to be the sum of the oxidation numbers is going to be 0. Now, potassium is a monatomic ion. So its oxidation number is going to be +1. That comes off the periodic table. Oxygen is almost always -2, and there are 2 of them. So we're going to do a little bit of algebra. So potassium is a +1, and we have 1 of them. We don't know chromium, that's what we're trying to find, so we put an X. oxygen is -2, and there are 2 of them. So 2 times -2. And the sum, since it's neutral, has to be 0. So it just becomes a little bit of algebra. Okay, we've got +1 plus x minus 4 equals 0. So we would have to add 4 to both sides, subtract 1 from both sides to get x by itself, x equals +3. So the oxidation number on chromium in this molecule is a +3. Now in other molecules, it might be something different than that, but in this molecule, it's a +3. So let's look at this one. This is a polyatomic ion. It has a charge of +1. That means the sum of the oxidation numbers has to add up to +1. Well, phosphorus can vary, and that's what we're trying to find. Hydrogen, because it's with a non-metal, is going to be a +1, and there are 4 of them. So again, we're going to kind of set up an algebra problem. We don't know phosphorus, that's going to be x. There are 4 hydrogens, and each hydrogen is a +4, and the sum has to equal +1. So x plus 4 times +1 equals +1. So that's x plus 4 equals +1. Subtract 4 from both sides, x equals -3. So the oxidation number for phosphorus in this ion is -3. So let's look at the next one together. Here's chromium again. It's not always a +3. Let's see if it's +3 in this particular ion. We don't know chromium. Oxygen is almost always a -2, and there are 4 of them. And this is a polyatomic ion. The sum of all the oxidation numbers has to equal -2. So we set up our algebra. X plus 4 times -2 equals -2. We don't know chromium, so there's our x. There are 4 oxygens, and they're each -2, so that's where that 4 times -2 comes from. And the sum has to equal the charge on the ion. So x minus 8 equals -2. Add 8 to both sides, x equals +6. So notice that the oxidation state for chromium in this compound is different than in this compound. Chromium varies in its oxidation number depending on what it's with. So we did 3 examples together. Let's see if you can do tetraphosphorus decoxide. Okay, we want to find out what the oxidation number on phosphorus is. Okay, we don't know phosphorus, but there are 4 of them. That's going to give us 4x. Okay, I agree, 5. So we've got 4x plus 10 times -2 equals 0. So that's 4x minus 20 equals 0. So 4x equals 20, x equals +5. And you do want to put the pluses and the minuses so you know which one it is. Don't just put 5. We should put +5. All right, so let's see if we can do this one. This is an ion now. Okay, we don't know what sulfur is. We do know what oxygen is. We know what the sum has to be. See if you can figure out what sulfur is. I'll give you a hint that it doesn't always have to be a whole number. Oxidation states if they're going to be fractions, make sure that they're the simplest fraction. Okay, so we've got 4x plus 6 times -2 gives us -2. So that's 4x minus 12 equals -2. So 4x equals 10. So x equals 5/2. There should be a plus sign in here. We really should have positives and negatives in there. All right, the last one should be kind of easy. Chlorine. It's not in a compound with other elements. What would its oxidation number be? I'll give you a hint. There's no math. okay? If you have atoms that are not in combination with other types of atoms in a formula, oxidation number is 0. Good. All right, so why do we need to know that? Because when we assign oxidation numbers to reactants and products in a chemical reaction, if the oxidation numbers don't change from reactant side to product side, it's not a redox reaction. But the oxidation numbers will change if electrons are being transferred from one substance to another, and that's what makes a redox reaction. So what does redox or oxidation reduction? Redox is just short for that, okay? What does it mean? Oxidation is defined as the loss of electrons by a species, okay, by an atom or an ion, okay? When it loses electrons, its oxidation number goes up because electrons are negatively charged. So if a species loses an electron, it's going to be left behind with more positive for its charge. Okay, reduction. Reduction is defined as the gaining of electrons. Well, if a species gains electrons and electrons are negatively charged, the reduction is the one where the oxidation number goes down. And another word for decrease or going down is reduction. So it literally is reducing the oxidation number when it gains electrons. And instead of saying oxidation reduction, we typically just say redox. The RAD is for reduction and the OX is for oxidation. It's just a shorthand way of saying it. Now, if you have an oxidation taking place in a reaction, you have to have a reduction to go along with it. They come in pairs. You can't have something in a reaction that's losing electrons, but have something else in the reaction gaining electrons. The electrons can't just disappear into thin air. They have to come in pairs. So let's look at this as a reaction, an example. We have some copper sulfate solution. It's this blue solution. And we add some iron solid to it. This reaction takes place. Okay, now we want to assign oxidation numbers. So first, since this is aqueous, we could break it up into its ions, copper ions and sulfate ions. And since this is aqueous, we could break it up into its ions, iron ions and sulfate ions, and the sulfate ions become spectators. So the net ionic equation looks like this, just a little bit easier to look at since the sulfate have nothing to do with the reaction anyway. Now, iron is a free element here. Its oxidation number is 0. Copper is a free element here. Its oxidation number is 0. But it's an ion here. The charge is equal to its oxidation number. And iron is an ion here, so its charge equals its oxidation number. So let's look at iron. It's going from a 0 to a +2. It's losing 2 electrons. So that means that iron is being oxidized. It's giving off electrons, and that's why its oxidation number is changing. Now let's look at the copper. It's going from a +2 to a 0. How's it doing that? It's gaining 2 electrons. And gaining electrons is reduction. So we have electrons being lost by the iron and gained by the copper ions. And that's how we end up with iron ions and copper atoms as our product. So this is a redox reaction. We have a reduction and an oxidation taking place. Now, kind of opposite terms that we might see. Since iron is being oxidized, it's referred to as the reducing agent. Okay, well, why? Well, iron is losing electrons, and when it loses electrons, it's causing copper to be reduced. So iron's the reducing agent. And when we look at the copper is gaining electrons. Well, the only way copper can gain electrons is if it's causing iron to be oxidized. So copper is the oxidizing agent. They're just opposites. The substance that's oxidized is the reducing agent, and the substance that's reduced is the oxidizing agent. So we can identify oxidation numbers, and then we can decide whether it's a redox reaction or not. Do the oxidation numbers change as we go from reactants to products? And then what's being oxidized and what's being reduced? So let's look at this as an example. First thing I want you to do, assign the oxidation numbers to sodium, it's a free element, to chlorine, it's a free element, and to sodium and chloride in this compound. Think about what the oxidation numbers are. So since sodium's a free element, it's 0. Since chlorine's a free element, it's 0. Sodium is a monatomic ion, so it's +1. Chloride is a monatomic ion, so it's -1. So now we look at this. Okay, well, sodium is changing its oxidation number. Chlorine is changing its oxidation number. It's a redox reaction. Okay, so, oops, wrong button. Since sodium is going from a 0 to a +1, it's gaining electrons, sorry, it's losing electrons, so it's being oxidized. And because there are 2 sodiums here and 2 sodiums here, they're each losing 1 electron, so there's 2 electrons total being lost. Where are those electrons going? Well, they're causing chlorine to be reduced. Chlorine's going from a 0 to a -1. Each chlorine is gaining an electron, but there are 2 chlorines that are each gaining an electron. Okay, now, loss of electrons is oxidation. Okay, we could kind of shorthand that as LEO, lose electrons, oxidation. Okay, gaining electrons is reduction. We could kind of shorthand that as GER, gain electrons, reduction. Now, this is kind of silly, and you can find all different ways to do this, but here's a little lion here. Okay, lions go, or Leo goes grr, is a way to kind of remember this. Lose electrons, oxidation, gain electrons, reduction. Leo goes grr. Okay, just a little trick to remember which is which. So I'm going to give you a minute. See if you can assign oxidation numbers to all of the species that are there. Decide whether it's a redox reaction. And if it's a redox reaction, what's being oxidized and what's being reduced. Okay, so the mercury is going from a +2 to a 0. Oxidation number is going down. It's being reduced. That means it's gaining electrons. And the oxygen is going from a -2 to a 0. It's being oxidized, or it's losing electrons. All right, so let's look at 4 quick redox reaction examples, and then we're going to take a quick break. So synthesis is a type of redox reaction. A synthesis reaction is one in which we have simpler things that we combine together to make one product. It's an example of a redox reaction. Okay, the bromine is going from a 0 to a -1. Oh, how did I unorder that? Oh, it's there. Never mind. I didn't see that. So it's being reduced. The gallium is going from a 0 to a +3, so it's being oxidized. So synthesis is an example of a redox reaction. Okay, decomposition is an example of a redox reaction. It's actually kind of the reverse of a synthesis reaction. In a decomposition reaction, we have one reactant that we break down. And when we assign our oxidation numbers, again, we're going to see that the oxygen is changing and it's being oxidized since the value's going up. Okay, there we go. And oxygen's also being reduced because its value is going down. The hydrogen is not involved this time in the actual exchanging of electrons. Okay, combustion is an example of a redox reaction. Okay, if we have some kind of hydrocarbon as a fuel and we react it with oxygen, we're going to produce carbon dioxide and water. It's a combustion reaction. If we look at carbon, its oxidation number is changing. And when we look at oxygen, its oxidation number is changing. So it's a redox reaction. Okay, our oxygen is being reduced and our carbon is being oxidized. Again, notice that you can't have one without the other. And then the last type of redox reaction is a single displacement reaction. And a single displacement reaction has some kind of element reacting with a compound, and this element displaces the ion out of the compound. And again, we're going to see that our oxidation numbers are changing from the reactant side to the product side. So our zinc is going from a 0 to a +2. It's losing electrons, so it's being oxidized. And the copper is going from a +2 to a 0 by gaining electrons or being reduced. So redox reactions are reactions in which the oxidation numbers change from reactant side to product side. And the 4 examples of redox reactions are synthesis reactions, decomposition reactions, combustion reactions, and single displacement reactions.